So, have you ever felt that jump from digital logic design, DLD, to microcontrollers feels like learning a completely new language? Yeah, you're not alone. It can seriously feel like you're leaving this comfortable world of predictable logic gates and walking up to this complex, intimidating black box. But what if I told you that you already have all the fundamental knowledge you need? Okay, let's dive in and reframe that black box into something you'll realize you understand pretty well. Right, so on the left, you've got this world you totally get. Timers, AND gates, OR gates, all the classics. But on the right, you've got this dense microcontroller with dozens and dozens of pins. The whole idea we're going to unpack here is right on this slide. A microcontroller is really just a massive collection of the exact same digital logic components you've already mastered. It's the same logic, just at a wildly different scale. So let's start peeling back the layers of that idea. We're going to see that the real difference isn't in the kind of logic you're using, but really in how it's all put together and, more importantly, the sheer scale of it all. Now, this is where it gets really interesting, because this slide translates all those intimidating microcontroller parts back into DLD terms. You know, the central processing unit, the CPU? Well, that's just a super fast finite state machine executing one instruction after another. All that memory, like your RAM and flash, that's just a huge array of D flip-flops, storing ones and zeros. And all those special modules they call peripherals, they're just specialized fixed logic blocks, exactly like the chips you probably used in your lab. Okay, this brings us to what I think is the single most important concept you need to grasp. We've figured out that the components inside are all familiar. The real magic, the big shift in thinking, is all about how we connect them. And this picture just illustrates that difference perfectly. In a normal DLD system, your connections are actual physical wires, right? You connect a switch to a logic gate with a little piece of copper. But in an MCU system, the connections between the CPU, the memory, the outside world, they're all soft-wired. The wires are actually just bits stored away in memory. Let's break that down a bit. In a hardwired DLD system, your logic is literally fixed by soldering. If you want to change what your circuit does, you got to get out the soldering iron and physically rebuild the whole thing. But in a soft-wired MCU system, well, the connections and the logic are programmable. So if you want to change what happens when you press a button, you don't rebuild anything. You just type a few new lines of code. And that is the magic of microcontrollers, this insane flexibility. So let's just throw out that old definition. From now on, here's what I want you to think. A microcontroller is simply a digital logic circuit where the wiring is stored in memory. That's it. It's not a mysterious black box anymore. It's a reconfigurable logic machine. All right, so with that new definition locked in our brains, let's get practical. We're going to build a cheat sheet, a direct translation guide that maps every core concept you already know from DLD straight to its counterpart in the MCU world. Let's start with a really simple one. Every digital system needs a heartbeat, right? A clock signal. In your DLD labs, you might have used some external chip for that. Well, inside an MCU, that same function is handled by a configurable piece of hardware, a peripheral, often called something like SysTick or the RCC. It's the exact same job, just a different name and a different place. Okay, how about getting input from the real world? A physical switch in DLD just gives you a high or a low voltage. In an MCU, that voltage gets read by a general-purpose input-output pin, a GPIO pin, and the state of that pin, that 1 or that 0, it gets stored in something called an input data register, which, as we already know, is just a group of flip-flops. See? You're not learning a new concept, you're just learning a new name for it. And here it is, the full cheat sheet, putting it all together. You can see how your physical circuit wiring becomes the logical flow of your code. An AND gate becomes a bitwise AND instruction in your software. And those finite state machine bubble diagrams used to draw, that's basically just a switch case statement in your C++ code. Keep this map in your head. You're not learning from scratch. You are just learning to configure the DLD components you already know how to use. Okay, so we've established that the MCU is packed with hardware blocks we actually understand. But that brings up a really big question. How does our software, our lines of code, actually reach in and take control of them? Let's explore that with an idea I like to call the mailbox analogy. This is the next big hurdle, right? The CPU can't just reach out and physically rewire the GPIO peripheral. So how in the world does it tell an LED to turn on? The answer is this concept called memory-mapped I/O. And the absolute best way to think about it is this mailbox analogy. The CPU talks to everything, RAM, its own code, and all those peripherals through memory addresses. To turn on an LED, the CPU doesn't do anything fancy. It simply writes a 1 to a very specific address, a special mailbox that happens to be physically wired to that LED pin. And this is it's a profound takeaway. From the CPU's point of view, there is no difference between saving a variable to RAM and turning on an LED. Both actions are just write this piece of data to this address. It's just that one address happens to be a bank of flip-flops used for storage, and the other is a bank of flip-flops that controls a pin driver. Let's zoom right in to make this crystal clear. When we say your code writes to a peripheral register, what is physically happening is that the CPU is setting the state of a group of internal D flip-flops. Again, it all comes back to the fundamental building blocks of digital logic that you're already totally comfortable with. Okay, so now we know how our code can control hardware, but we really need to talk about when it does it. Because the most obvious way to wait for something to happen in the real world, well, it leads to a really common and sometimes a very dangerous problem. The most basic way to wait for an event, say a button press, is called polling. Your code literally enters a loop, constantly checking a status register, just asking, did the button get pressed yet? How about now? Did it get pressed yet? It's the software version of a kid in the backseat of a car yelling, are we there yet? Over and over again. And the crucial part is, while the CPU is stuck in that loop, it cannot do anything else. Now, why is this such a big deal? Let's raise the stakes a lot. Imagine you're designing a pacemaker. Its main job is to keep a heart beating at a nice, steady rhythm. But what if you also added some code that polls for a doctor to press a configuration button? If your code gets stuck in that polling loop just waiting, what happens to the critical life-saving logic that's supposed to be pacing the heart? It stops. The processor is completely tied up just waiting for that button, and it can no longer send out the pulses needed to keep the heart beating. The result is, well, it's catastrophic failure. Blocking your code like that is incredibly dangerous in any real-time system. So clearly, we need a better way. And thankfully, the hardware gives us an incredibly elegant solution to exactly this problem. And that solution is called an interrupt. Instead of the CPU constantly badgering the hardware essentially taps the CPU on the shoulder when something important happens. When the button is finally pressed, the hardware itself forces the CPU to pause what it's doing, jump to a special function to handle that button press, and then it seamlessly returns right back to its main task. The main loop is never, ever blocked. And this chart shows you exactly why this is so critical. The response time you get from a polling loop is all over the place. It's jittery and unpredictable. It totally depends on where the CPU was in its loop. But an interrupt? It gives you a precise, consistent, and totally deterministic response time. In something like a medical device, a late response is a wrong response. Interrupts aren't just for convenience, they are absolutely essential for guaranteeing safety and timing accuracy. So let's bring it all the way back to the beginning, that intimidating black box. It's really just a sea of familiar components, gates, flip-flops, state machines, all connected with these programmable soft wires. You are not learning a new field from scratch. You're just learning a new and incredibly powerful way to configure the hardware you have already mastered. So the real question is, now that you know how to speak its language, what are you going to build?